Hello dear students, welcome to the lecture 2 of laser. In this video, we will be learning about different types of lasers. We will see what is a 3-level and a 4-level laser and also different examples of lasers such as ruby laser, helium neon laser, the carbon dioxide laser, the dye laser and the semiconductor laser. Now let's see what are type of lasers. There are basically two types of lasers based on the lasing levels, and that are 3-level laser and 4-level laser. In our previous lecture video, we have discussed that to make a good laser, at least 3 energy levels is important. Only some atoms which can offer 3 energy levels such that one excited state with a very small time period, a metastable state with a comparatively larger time period, and a ground state can only give lasing. Such an atom or such an element can only achieve population inversion. So to make a laser, at least 3 energy levels are important. So in 3-level laser, at least 50% of the atoms or electrons or whatever materials have to be in the excited state or in the metastable state to achieve population inversion. Therefore, it requires very high power to maintain such lasers. Also, when it starts lasing, the electrons or the atoms in the metastable state will start falling into the ground state and the population inversion no more holds. Therefore, it is not possible to sustain population inversion in case of 3-level lasers. Therefore, it can work only in pulsed mode. That is, constant pumping is needed and also high power of pumping is needed because more than 50% of atom have to achieve energy and go to the metastable state. But in the case of 4-level laser, we have 4 different levels, and the lasing, the time between the first 2 levels, that is, the time gap between the level E4 and E3 and also the level E2 and E1 are very small. That is, between E4 and E3, the atoms will spontaneously degenerate. There are very less time period in the level E4 and also very less time period in the level E2. When atoms are excited to level E2, it will spontaneously degenerate to E1. But E3 has a time period which is good enough to hold metastable state. Therefore, E3 is the metastable state and the lasing happens between the transition that happening between the E3 level and the E2 level. When pumping happens, the ground state atoms, that is atoms in the E1 state, can be excited to any states E4, E3 and E2. But E4 has a very less time period, so it spontaneously degenerates to E3 and it stays there for a longer period because E3 is the metastable state. The atoms which are excited to E2 state spontaneously degenerate to the ground state, and both these happens non-radiatively. Therefore, the atoms will accumulate in the E3 level, and after completing the lifetime in the E3 level, the atoms will come down coherently to the E2 level, just as lasing happens in the last video we have discussed. So in this case, more than 50% of atoms shouldn't be excited to a higher energy state. Only the atoms in the E3 have to be greater than E2. Therefore, the moderate power is required to make this laser work. And also, it is easy to maintain the population inversion state because the lasing happens between E3 and E2. Therefore, E3 level will have a comparatively good number of excited atoms over there, which degenerate from the E4 level. Therefore, this atoms, a 4-level atom, can give continuous waves because it is easy to maintain its inverse population inversion state. Now let's look into our first example, that is a ruby laser. A ruby laser is a solid state laser, and the active medium which is used in the ruby laser is a crystal which is made up of aluminum oxide doped with 5% of chromium 3 plus atoms. Therefore, the lasing level here is provided by the chromium 3 plus ions, and the lasing levels are provided by chromium 3 plus ions, which provide 3 level laser. It will provide 3 energy levels. So the ruby laser is a 3 level laser. Since it's the 3 level laser, we expect only it to work in the pulsed mode. And the color of the laser we achieve from a ruby laser is red with a wavelength of 6943 angstrom. For a ruby laser, it has a laser medium which is covered by 2 mirrors, one fully reflecting mirror and one partially reflecting mirror. It is surrounded by a flash tube, a xenon flash tube, and the pumping here is optical pumping. That is, light is provided to excite atoms to a higher energy state. Therefore, a xenon flash tube is used here to pumping, and the population inversion is obtained in the energy levels of chromium 3 plus atoms. A xenon tube is covered. A xenon tube is used to make a population inversion possible. Here you can see that this is a ruby laser, and inside the ruby laser the xenon tube just flashes. When the xenon light tube flashes, the atoms, the chromium atoms inside the active medium absorbs this light energy and go to a higher excited state. When the xenon flashes, the chromium ions go to a higher state, and it stays there at the metastable state and comes down to the ground state coherently to produce lasing. Therefore, it has a xenon tube which is wound helically around a tube of active medium which contains the ruby, and it is an active medium. Towards the end of the active medium, it is coated with aluminum or silver, and that act as the mirror. Therefore, active medium, the end of the tube of the active medium is coated by aluminum or silver, one part of which is partially reflecting, and out of that portion the laser beams comes out. A cylindrical reflector containing a liquid nitrogen is used here to make to act as a coolant, because xenon light are used, and during lasing there is a high possibility for to the medium to get heated up. Therefore, we use liquid nitrogen as a coolant, and we use a spiral xenon flash tube to maintain pulsing. And here, since it's a 3-level laser, we will get laser only in pulsed mode. We cannot achieve continuous laser, only pulse mode is obtained. And now let's see how a ruby laser works. Now, when the xenon flash lamp flashes, it receives the UV and the yellow light which is absorbed by the chromium atoms or the chromium ions which is present in the active medium. And now the chromium ions will get excited from the ground state to a higher energy state, E2, which is in the energy bands. Now it will we have all these energy state in terms of their energy bands and not as energy levels. We have already discussed this, that the energy levels appear as energy bands because of natural broadening. Therefore, the excited state as well as the metastable state will exist as energy bands in every atoms. Therefore, the pumped electron or the excited electron will go to an energy band, not to an energy state. Now, these whatever which is being pumped will reach the excited energy band or the metastable energy band. And from these two levels, the excited atoms will non-radiatively decay to a metastable energy state. Not band, it will radiate to a single energy state, that is a metastable energy state. Since it's a metastable energy state, the atoms can live there for a longer period, and after completing the time period in the metastable state, one or two atoms will degenerate spontaneously. It will generate a photon. That photon will reflect back and forth through the medium, and it will cause stimulated emission of other atoms, other excited atoms in the metastable state. So every atoms will coherently emit photons, and these will cause lasing. And this is how a ruby laser works. And lasing happens only for a millisecond pulse. Only for a millisecond, so it pulses. We cannot get continuous laser because constant pumping is needed to maintain the population inverse state. Therefore, while pumping, the electrons will go to a higher energy bands. After that, they will decay non-radiatively to a metastable state, and from there they will stimulatedly emit to the ground state to give laser. Now let us look into the next type of laser, that is helium neon laser. A ruby laser was a solid state laser, but a helium neon laser is a atomic gas state laser, and here the active medium is helium atoms and neon atoms in a ratio 10:1. Here the laser levels are provided by the neon atoms. The neon atoms gives the necessary laser levels. This is also a 4-level laser. All these 4-level energy states are provided by the neon atoms itself. And the color which we obtain from the helium neon laser is a red color of a wavelength 6328 angstrom. This is a prototype of a helium neon laser. So inside the active region, the helium and neon is filled in 1 mercury pressure. It has an anode and a cathode to give pumping. Here the pumping is through electrical discharge. In the case of ruby laser, we have seen the pumping was through optical, and here the pumping is electrical. So to give electrical discharge for pumping, we have a cathode and an anode here. Again, we will have a pair of plane or concave convex mirrors to achieve for the photons to reflect back and forth through the medium. One of the mirror will be partially silvered. Helium atom and the neon atom has similar energy levels. That's why we have used the helium neon gas mixture. The excited states of helium atom and the neon atoms falls in the same energy state. Therefore, helium atoms helps the neon atom to achieve population inversion. We have seen that the neon atom is the one which provides us with the latent energy state, but the helium atoms helps the neon atom to achieve the inversed population state. Since this is a 4-level laser, we can achieve continuous laser without high energy pumping. With low energy pumping itself, we can achieve a continuous laser. Now let us see how a helium neon laser works. When there is an electrical discharge, the helium ions which are in the ground state will excite to its excited states. It has two excited states, and these two excited states are similar to the excited states of the neon atom. Once it reaches the excited state, these excited helium atoms will collide with the ground state neon atoms. And on collision, the ground state neon atoms will absorb energy from the helium atom, and it goes to the energy levels 5s and 4s. This type of energy transfer is called resonant transfer. The resonant transfer is happen because of collision energy transfer. Once it reaches the energy state 5s or 4s, the atoms which is in the 5s levels, the 5s here is the metastable state. Now the atoms which is in the 5s level the 5s level is the metastable state level. Therefore, the atoms will accumulate in the 5s level. After completing the time period in the 5s level, the atoms will stimulatedly degenerate to the 3p state. Here it comes to the 3p state, and this provides us with the laser light, which is of 632.8 nanometer or 6328 angstrom. Therefore, the laser comes out from the radiative transfer which happens between the 5s level and the 3p level. Here 5s is the metastable state. Now another lasing will also happen, another transfer from 5s to 4p and also 4s to 3p can also occur, because atoms can accumulate in the 5s and 4s level and it can degenerate to 4p and 3p levels. But in this case, the degeneration is non-radiative. That is, we cannot see the radiation, so this will not affect the lasing beams. The laser, the photons is absorbed, attained only by the lasing between the levels 5s and 3p. Once all these atoms comes and accumulate in the 3p state, then it will non-radiatively transition, it will transfer to the 3s state spontaneously. Then after that, reaching the 3s state, since the atoms are in constant collision with each other and also with the walls of the container, it will lose energy while collision, and through diffusion through the walls, the energy is released and it comes to the ground energy state, and this is a radiation-less transfer. So let me repeat. Once the helium atom will absorb energy from the electrical discharge, it will go to its higher energy states. These higher energy states are similar to that of the excited states of the neon atom. Therefore, the excited helium atoms will collide with the neon atoms in the ground state, and there occur a resonant transfer of energy, and the neon atoms will get excited to its excited states 5s and 4s. Here 5s is the metastable state, therefore atoms will accumulate in the 5s state. After completing a lifetime in the 5s state, the atoms will stimulatedly and radiatively degenerate to the 3p state, giving the laser light of a wavelength 632.8 nanometer. And all other transition, that is from 5s to 4p and 4s to 3p, are non-radiative, that is the radiation is not found. And the atoms, after accumulating in the 3p state, they will radiate spontaneously to the 3s state, so it will not account for the laser. And after reaching the 3s state, due to its collision with the walls of the container, it will lose energy and come to the ground state. And this is how the helium neon laser works. Now let us see the next type of laser, that is a carbon dioxide laser. A helium neon laser was an atomic gas laser, while carbon dioxide laser is a molecular gas laser. In case of carbon dioxide laser, the active medium is carbon dioxide molecule, nitrogen molecule and helium atom in the ratio 1:4:5. Here the laser levels are provided by the rotational and the vibrational state of carbon dioxide molecules, and similar to helium neon laser, here the nitrogen molecule and the helium atom helps in attaining the population inverse state for the carbon dioxide molecule. We will get an infrared or near red radiation in case of a carbon dioxide laser with a wavelength 9.6 micrometer and 10.6 micrometer. The carbon dioxide is also a 4-level laser, therefore we expect a continuous laser in this case with a very low stimulation or pumping. Carbon dioxide, the vibration modes. Carbon dioxide is a molecule with one carbon atom in the center and 2 oxygen atoms. And this carbon dioxide, instead of moreover having excited electronic energy state, it has vibrational energy state. There are 3 different vibrational energy state possible for a carbon dioxide molecule. That is symmetric stretching. Symmetric stretching is attained when 2 oxygen molecules are symmetrically away from the carbon molecule. This is symmetric stretching. Or it can be due to bending. Or it can be due to asymmetric stretching. There are 3 types of vibrational modes happening in a carbon dioxide molecule. One is symmetric stretching, another is symmetric bending, and another is asymmetric stretching. As you can see in the figure, the vibrational energy levels caused due to these 3 are different. Therefore, it will provide 3 different energy levels, and the transition between these 3 energy levels provides us the lasing. Therefore, the laser energy levels are provided by the vibrational modes of the carbon dioxide atom. One electronic state, and this vibration lasing happens in the lowest electronic state. The vibrational and the rotational sub-energy states of the lowest electronic states provide us with the laser energy levels. Here the nitrogen atom and the helium atom helps in achieving the population inverse state. A carbon dioxide laser is a very efficient laser because it can give a good intensity of a laser with a small energy used for pumping. Now let us see how do a carbon dioxide laser works. As I said, the energy levels, all these vibrational energy levels are contained inside the ground state electronic energy level. And similar to what we have seen in helium neon laser, the nitrogen, the energy levels, excited energy level of nitrogen is similar to that of the excited energy level of carbon dioxide. That is why the nitrogen can help the carbon dioxide in achieving population inversion. Similar to helium neon laser, while pumping, the nitrogen atoms in the ground state will achieve energy, will gain energy and go to the excited state. After reaching the excited state, it will transfer energy through resonant transfer, that is through collision, to the carbon dioxide molecules. So, the carbon dioxide molecules will come to the higher energy state, and the higher energy state which they are coming as the asymmetric stretching state. As we have said, we have three different states available, and that are mentioned as V00, 0V0 and 00V for symmetric stretching, bending and asymmetric stretching respectively. This is how we denote the energy state. This is how we denote the energy state. That is, if it is first level of symmetric stretching, then it will be 100. If it is the second excited symmetric stretching, then it will be 200. For the ground state bending, it will be 010, and ground state asymmetric stretching, it will be 001. These are the notations we use to specify the energy levels. So, here the nitrogen atoms will excite and will collide with the higher carbon dioxide atoms, and the carbon dioxide atom will reach its higher energy state. And this higher energy state is the energy state 001, which is provided by asymmetric stretching. Is the first level of asymmetric stretching, not the ground level, the first excited level of asymmetric stretching, and the atoms will come to the 001 level. After reaching the 001 level, it maintains there because this is the metastable state. Therefore, the atoms can accumulate in the metastable state. After completing the lifetime in the metastable state, it can transfer radiatively to two different states, that is 0 to 0 and also 100. The two energy levels 0 to 0 and 100. The 0 to 0 state is the bending state, and the the second excited bending state, that is why 0 to 0, and it can come to the symmetric stretching state, the first symmetric stretching state 100. These two transfers are radiative transfers, and the radiations are 10.6 and 9.6 nanometer micrometer laser micrometer waves are produced, photons are produced, and this causes the laser. Here the lasing has two different laser transitions with two different energy states. Therefore, we can attain a combination of waves that has a wavelength 9.6 and 10.6 micrometers. And later, coming on to this state, they will fast decay to non-radiatively, it will decay to a lower energy state, and that is 010 bending state. 010 bending state, it will non-radiatively transfer to 010 bending state, and after that it can come to the ground state by fast decay, and that is also a non-radiative transfer. So let me repeat. On acquiring enough pumping, the nitrogen atoms will get excited and go to a higher energy state. It will collide with the carbon dioxide molecules. The carbon dioxide molecule will go to a higher energy state, which is its asymmetric stretching state, and it will stay there for a longer period. After that, it will make radiative transfer, that is laser transition to two different states, that is 020 bending state and 100 symmetric stretching state. And we will get laser lights of wavelength 9.6 and 10.6 nanometers respectively. After that, they will decay non-radiatively to their lower energy state 010 and then to the ground state respectively. Now let us see the next type of laser, that is a dye laser. So far we have seen the solid state laser and the gaseous state laser. The dye state here is a liquid state laser. Here the active medium is an organic dye which is dissolved in ethyl alcohol, glycol or water. The energy states, the laser levels are provided by the vibrational energy levels of different electronic states. In the last, that is carbon dioxide, the transitions was happening only in one electronic energy states. Here the transitions are happening in the different electronic energy state of the dye, and the vibrational energy levels within the electronic state plays a role in this. And the color we obtain is yellow-red when we use the dye rhodamine 6G, and we will obtain blue-green color when we use the dye coumarin. Now, the electronic states, the dye has different electronic states. A dye can have singlet electronic state, that is only one energy level in one state, or it can have triplet energy state, that is three energy levels having the same energy will form a triplet energy state. Therefore, the dye can have singlet energy state as well as the triplet energy state. And the transition between the singlet energy state is which is needed for us. Now, while pumping, these S0, S1, S2, T2, T1, all these are electronic energy state, and the small lines which you see in between are their rotational and vibrational energy states, which are the sub-energy states of these electronic state. So while pumping, the atoms in the lower electronic energy state will get excited to a higher electronic energy state S1, and in there they will have different vibrational energy state, and since it get excited to any of the vibrational energy state in the S1 energy state, it will make non-radiative transitions towards the lowest vibrational energy state of the S1, that is the lowest line. Towards the lowest line, it will make non-radiative transfers and reaches this point. And this energy state here is the metastable state. And the transition which happens from the S1 to the S0, any energy levels or maybe some of the higher energy levels of S0, gives us the lasing. Therefore, what happens is on pumping, the atoms in the S0 state will go to the S1 state. And there are many possibilities of acquiring S1 state. So all these atoms in the higher vibrational energy level of S1 state will non-radiatively transition to the last vibrational energy state, where it stays for a longer period and it will achieve population inversion. After that, it will go for spontaneous emission from this lowest energy state to any of the higher energy state of S0. There are also possibilities for this S1 to make a transition to T1 state through T1 state. And this will reduce the population in the S1 state, and this affects the lasing because we need high population inversion. So to avoid this, to reduce the transition to T1 state, we add oxygen so that the time period of the T1 state is comparatively much reduced, so that we can achieve population inversion in the lowest vibrational state of the S1 electronic state. This is the last type of laser we are going to learn today, that is the semiconductor laser. So the semiconductor laser is somewhat different from whatever we have learned so far, because in the last examples, what we had was one atom or one molecule which provides us with energy levels, 3 or more energy levels, such that we can attain population inversion. But in the case of a semiconductor, the energy levels are provided by the valence band and the conduction band of the semiconductor itself. That is, individual energy level of the atoms involved doesn't matter. Only the valence band and the conduction band of the semiconductor as a whole is what which gives us the laser energy levels. Here there are much more leniency because we do not need to use mirrors. We can cut crystal in such a way that the end of the crystal itself acts as mirrors. Here the photons are produced by the recombination of holes and electrons in the active region. Hope you remember what is a semiconductor. Here we can use a PN junction diode. A PN junction diode is used. Therefore, we have active region, that is a depletion region, and also one side we have a larger number of electrons and in the another side we have a larger number of holes. Therefore, when the holes and the electrons combine in the depletion region, they will produce photons. And these photons can interact with the semiconductor in two ways. Either it can interact with the valence electron, and this valence electron then will absorb energy from the emitted photon and can go to the conduction band, and this causes stimulated absorption. Or else the photons emitted can interact with the electrons in the upper conduction band, and the electrons there can radiatively transfer, that is stimulated emission can occur from the upper conduction band to the lower valence band. Therefore, the two ways in which the photons, the recombination photons can act, either it can go for a stimulated absorption while interacting with the valence electron, or stimulated emission while interacting with the conduction electrons. We know that at normal temperature, normal conditions, the valence electrons are much higher than the conduction band electrons. Therefore, under normal conditions, the stimulated absorption is highly possible than the stimulated emission. But what we need is stimulated emission for a laser. Therefore, we will keep PN junction diode in the forward biased state. In the forward biased state, we can attain stimulated emission to be greater than stimulated absorption. To attain population inversion, the carrier, that is electrons or holes, are injected into the junction region or the depletion region, and this will help in attaining the population inversion. After that, pumping occurs, and when the diode is forward biased, it will definitely achieve population inversion, and after achieving population inversion, similar to all other lasers, it will go for lasing, and the laser light is amplified just by stimulated emission and reflection between the mirrors. So dear students, in today's lecture we have learned about different types of lasers. There are different types of lasers. There are 3-level lasers, 4-level lasers, and also we have learned 5 different examples. In the coming video, we will learn about the characteristics of a laser beam and its applications. See you in the next video. Thank you.